Hello, my name is Alexis Mesa. This is a video for my image processing class. This video is going to consist of a presentation followed by a 4 video MATLAB demo. My project consists of a CAN-shift algorithm, which is an improvement from a main shift tracking algorithm. So the motivation behind it is to find a filter which is able to do face tracking and simple object tracking or block tracking. One way of doing that is the Minship algorithm, which through the years has provided a reliable way of tracking object whose appearance is defined by color. However, it's not limited to that. It could use just the edge or the texture of the image. To explain a little bit about Minship algorithm, the idea is that it takes the intensity at the xy coordinates and divides by the distance from the center of the feature window, which is the blue line. This results in a new center of mass with a displacement seen by this arrow, which is the mean shift vector. Now, the motivation of a camp shift is that the main shift creates many errors since the window does not change in size. For example, if the window is too small, then um, the prediction will jump inside the object of interest since the window is just a small subset of the whole object. Um, Also, if the window is too big, the algorithm will get confused and will not know what object is tracking, if it's the ball or the background or the tennis ball. Hence, to fix that, uh, uh, I propose a continuous adaptive shift algorithm, main shift algorithm, which changes the windows according to the size of the object tracked. So how does the cam shift works? The first thing it does is it asks the users to target to pick a target to be tracked. Then it produces a histogram based on the hue of the whole image. Then increases the region of interest. It iterates the main shift algorithm until it converges. In my algorithm, it converges to it converges when it reaches 1 pixel 1 pixel error. Then it uses the calculation step 4 to produce a new size of the window, and then it jumps to step 4 to keep calculating the next frame until the video is over. In order to do this, the zero moment is calculated by summing the xy coordinates of the intensity. Then the first moment is computed by multiplying the x and y components uh, of the image intensity. Then they're normalized to give a centroid, and the window size is just the square root of the zero moment multiplied by a ratio which was experimentally obtained. Now, why do I pick hue? The reason is that it behaves really well at color detection. The hue, for example, this is a red object, and this is a hue um, image of the object. As you can see, it's really easy to distinguish between that and the background. In fact, once the region of interest, which is picked within the black box, is 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 calculated, everything else on the background is is omitted, hence it's turned black. But there's an issue on calculating the region of interest. I made an optimization about it because usually what is done is that all the pixels, the intensity of all the pixels within the region of interest is there's sum and divided by how many pixels. Basically, the mean is obtained, and in cases such as this, produces good results. However, in cases such as where the user picks a lot of background space or space that is not within the that is not inside the object of interest, it produces bad results, such as this. The reason why is that the background mean hue is a lot lower than the tracking object. Hence, once you combine, because of the mean, these two, you get an undesired resultant hue. To alleviate the problem, instead of using the mean, I use the median, since it is assumed that the user is able to select at least 50% of the object. Hence, the window consists of at least 50% of the object of interest. Now, a few things about this algorithm is that it continuously adapts the window to increase to fit the size of the object, so that it encompasses the whole object, as long as the object has a contiguous color. Furthermore, another really important characteristic of this algorithm is that it's able to compensate for objects that are moving in different depth. Hence, in a mean shift algorithm, if the objects move in different depth fields, the algorithm will fail, because the window will start picking up, for example, over here, will start picking up background pixels, and will say, oh, I lost the target, when in fact is within the target. Hence, this algorithm is able to change the size as it moves towards away from the camera. As you can see, it moves the feature window, it gets reduced and it moves away, and as it moves forward, it starts increasing in size. Hence, the CAM-shift algorithm shows a significant advantage. In conclusion, the CAM-shift algorithm shows a significant advantage over the mean shift algorithm with little computational overhead. Only 2 additional square roots and 2 multiplications are needed in order to obtain a continuously adapting feature window, which are just these 2 over here. Hence, it's a small price to pay for such an improvement. Now I'm going to do a demo. Basically, there are 4 different videos. The first one shows how the CAM-shift provides the same capabilities as the mean shift algorithm. Demo 2 shows some interesting characteristics about the CAM-shift algorithm. Demo 3 shows the same as Demo 1, but with a faster moving object. And Demo 4 shows how the adapting window size works. So let's go to MATLAB. Over here I have my CAM-shift algorithm and a function that basically selects the window, the feature window, and I have inside my demos, I have my Demo 1 video, Demo 2 video, and so on. So let's run it. So what it's basically doing right now is extracting all the frames, and it's asking me to select a feature window. So I'm going to select this as my tracking object. So this should close automatically. However, this computer is a little bit slow, so it doesn't refresh the screen. So right now it's doing the calculations of the CAM-shift algorithm, and the movie is ready. Now if I hit play, it tracks correctly. the object. Now it's extracting the second frames. Now it's asking me to select a picture window. I'm gonna select this. I close that. Now it's doing the calculations for the second one. Then this is interesting because if you notice in that specific frame the marker is moving horizontally. However, the camshaft does not notice a lot of changes. This is now it's asking me for the third video, a faster moving object. I'm gonna select the ball for this one. The reason that happens is that since the camshaft only sees a subset of the whole market, it only moves if the background just changes. Since the market is moving horizontally, the background is not changing, and it doesn't pick up that movement. Now this takes a little bit longer because this image, this video is about 30 seconds long. So here it is. You see how the window follows the tracking cursor? Now for some reason it didn't